This presentation is about balancing chemical equations. Some basics about chemical equations. So this, what I've written here is a basic chemical equation, and I need to emphasize some things because I'll use these terms freely. The things that are on the left side of the arrow are what we call the reactants. So in this case, magnesium and oxygen are reactants. The things on the right side of the arrow are called products. In this case, magnesium oxide is the product. So we could say that when I react magnesium with oxygen, I get magnesium oxide as a product. Another thing to note is that in many chemical equations we'll have these little letters next to each of the substances. These are the state subscripts. So S stands for solid, G stands for gas, and this equation doesn't contain it, but L would stand for liquid, and occasionally we will see AQ, and AQ stands for aqueous, and aqueous is just a fancy word for dissolved in water. The numbers out in front of each of the substances we call coefficients, and we can manipulate the coefficients to balance our equation. We can never change the subscripts. So O2 has a subscript. The 2 is a subscript telling how those atoms are combined with one another. But I can freely change the elements of the recipe, the coefficients out front. So in this case, the coefficient for magnesium is 2. It doesn't appear that there's a coefficient for oxygen, but anytime there isn't a coefficient in front of a substance, that means that it should be 1. We just take the shortcut and don't put that in. And then the coefficient for magnesium oxide is 2, and we'll talk about why those numbers work out for us. And the reason that the coefficients have to work out is because of the concept of conservation of mass. And you probably heard this way back in 8th grade or 9th grade science somewhere, where you were told that matter can't be created or destroyed. So sometimes this is called conservation of matter. So basically, the mass of whatever I start with has to be reflected in the mass that I end up with, or in the way I look at it is all of the atoms that I put into a reaction have to be present as products. So any elements that I have as reactants, I have to find the same quantity of those elements as products. And I can look at this right away and see that that isn't the case. So certainly the iron atoms aren't in balance, the oxygen atoms aren't in balance, the hydrogen may or may not be. So we'll talk about how to get these balanced in the next few slides here. Okay, so we're going to balance that equation, and I always do this by inspection, working carefully left to right in this. So I can see that on the reactant side, the Fe3O4 substance here, I've got 3 iron atoms, but only 1 on the product side. And the way we fix this is that I put a coefficient of 3 out in front of the iron atoms on the product side. So now my iron atoms are balanced. The next thing I look at is the oxygen atoms in the iron compound on the reactant side. It's got 4 oxygen atoms, so I need 4 oxygen atoms on the product side. Each water has 1 oxygen atom. So if I had 4 water molecules, I would have 4 oxygen atoms. So I'm going to do that. I'm going to put a 4 out in front of the water. So now my irons and oxygens are balanced. I'm going to move to the hydrogen. So on the reactant side, I have 2 hydrogen atoms. On the product side, I have 4 water molecules. Each water molecule has 2 hydrogen atoms. So 4 times 2 gives me 8. So I've got 8 hydrogen atoms on the product side. The way to fix that is to put a 4 out in front of the hydrogen on the reactant side. So I should be balanced, and I always kind of sweep through a second time. So I've got 3 irons, 4 oxygens, 4 oxygens, 8 hydrogens, and then again 8 hydrogens. So everything appears to be in balance. Okay, let's talk about combustion reactions. This is a combustion reaction, so if I have a compound that is principally made out of carbon and hydrogen and I react it with excess oxygen, I always expect to get carbon dioxide and water. So as long as I have an excess of oxygen, I'm going to fully oxidize the carbon and hydrogen. So when I balance these, I see that I've got 4 carbon atoms. So to fix that, I'm going to put 4 on the product side in front of the carbon dioxide that contains the carbon atoms. I've got 10 hydrogen atoms on the reactant side in the butane molecule. And I've got 2 on the product side in water. So if I multiply the water by 5, I get my 10 hydrogen atoms that I needed. And then I go to counting up the oxygens, and I see that on the reactant side I've got 2 oxygen atoms. On the product side, both carbon dioxide and water contain oxygen. So I have 8 oxygen atoms in carbon dioxide. 4 times 2 is where I get that. And then 5 times 1 for the waters. So I've got a grand total of 13 oxygen atoms on the product side. And I always refer to this as an odd-even situation. And the way to kind of work this out is to make use of that one term that you learned way back in math sometime, the least common multiple. So the least common multiple of 2 and 13 is 26. So when I adjust atoms here, I'm going to adjust so that each side has 26 oxygen atoms. To do that, I'm going to put a 13 in front of the oxygen molecule. So 13 times 2 is 26. And that would mean that I would multiply the other side by 2. So everything that contains oxygen is going to have twice as many of those molecules. So I'm going to cross out the 4 and cross out the 5, and I multiply that by 2, so now I've got 8 carbon dioxide molecules, and now I have 10 water molecules. And that inevitably is going to blow the balancing for my carbon and hydrogen. So if I sweep back, I can see I now have 8 carbon atoms on the product side, and I only have 4 on the reactant side, so I'm going to have to double that. So I'm verifying, so I put 2 there, and then everything works out. So sometimes we have to go back and forth a couple times, and I know that many combustion reactions have this odd-even situation. So keep an eye out for that. Another scenario that pops up is when I have reactants and products that contain polyatomic ions. As long as those polyatomic ions stay intact on the reactant and product side, I can balance them as a whole unit. So we're going to balance polyatomic ions together. So the carbonate is in sodium carbonate on the reactant side. I've got iron carbonate on the product side, or more correctly, I guess, iron 3 carbonate. On the reactant side, I've got iron 3 nitrate, and then I end up with sodium nitrate on the product side. So I can balance those polyatomic ions as one unit. So in my first step here, and I got a little bit ahead of myself, I have 2 sodium ions on the reactant side, and I only had 1 sodium ion showing on the product side. So if I just double that, I'm going to end up with my sodium atoms balanced. I'm going to move on to the carbonate. So in sodium carbonate, I have 1 carbonate, but in the iron 3 carbonate, I have 3. So I'm going to throw a 3 out in front of the sodium carbonate to get that all balanced out. I know right away that I just messed up my sodiums, so I'm going to sweep back. I now have 6 sodium atoms or ions on the reactant side, and I need 6 on the product side, so I'm going to get rid of 2, and I'm going to put in a 6 there. So my sodiums are now balanced. Let's move on to iron. So on the iron count, I have 1 iron atom on the reactant side and 2 on the product side. So that's an easy fix. All I do is put a 2 in front of the iron, and then I should be good. And then when I look at the iron nitrate, if I multiply both, or the nitrate by 2, so each formula unit of iron 3 nitrate has 3 nitrate ions, and I have 2 of them, so that means I have a grand total of 6 nitrates. I look over to the product side, I've got a 6 in front of sodium nitrate, so that means I have 6 sodiums and 6 nitrates, so that's going to work out, and that ends up being balanced. I went through and verified that. So As kind of a prompt to get you to do some of this or on your own, and these are the type of things that mastering chemistry is really poor at, working with balanced chemical equations and to a certain extent working with molecular structure. So I would like you to work on this worksheet and turn it in when you are finished with it.